The flow of the cosmos is the dance of forces. With the dreams of neutrino fields and Higgs. Where electromagnetism meets quantum whispers. And we're ensnared in the murmurs of gravity. In the shadows of antimatter and dark. Lie the hidden truths waiting to embark. The breath of dark energy paves unknown ways. While string theory guides our dreams ablaze. The universe's melody, diverse in its tune. As each force converges under the cosmic moon. One universe, one tale to be told. A unified saga of mysteries unfold. Today in our 21st session of Cosmology 101, we'll delve into the fundamental forces that drive the universe and their theoretical underpinning, string theory. Remember, your likes and subscriptions greatly empower our video production. Neutrinos and the hypothetical neutrino field. While light propagates as a vibration of the electromagnetic field, neutrinos are thought to be influenced by a hypothetical field called the neutrino field. However, the existence of the neutrino field has not yet been experimentally proven. The neutrino field. The neutrino field is a hypothetical field proposed to explain the interactions between neutrinos. It is similar to the electromagnetic field, but much weaker and with different properties. Characteristics of the neutrino field. 1. Extremely weak force. The strength of the neutrino field is more than 10 to the power of 38 times weaker than the electromagnetic force. 2. Long-range interaction. The neutrino field can operate over very long distances. 3. Mass generation. The neutrino field may play a role in neutrinos' mass. Evidence supporting the existence of the neutrino field. 1. The solar neutrino problem. Observations showed that the number of neutrinos produced in the Sun is less than expected. 1. This could mean that some neutrinos are converted into other types of particles as they travel from the Sun to Earth. 1. This conversion can be explained by the existence of the neutrino field. 2. Neutrino conversion on Earth. Observations have shown that some neutrinos produced on Earth are converted into other types of particles. 2. This conversion can also be explained by the existence of the neutrino field. 3. Quantum mechanical effects. The neutrino field is affected by quantum mechanical effects. 3. This means that the neutrino field has both wave and particle properties. Research to confirm the existence of the neutrino field. 1. Direct detection of the neutrino field. Scientists are conducting experiments to directly detect the presence of the neutrino field. 2. Neutrino conversion research. Scientists are studying neutrino conversion to understand the properties of the neutrino field. Neutrino mass. 1. The neutrino field is thought to be responsible for giving neutrinos mass. 2. Neutrinos were once thought to be massless, but recent research suggests that they have a very small but non-zero mass. Neutrino spin. 1. The neutrino field is necessary to explain the spin of neutrinos. 2. Spin is the intrinsic angular momentum of a particle. Neutrino mixing. 1. The neutrino field is necessary to explain neutrino mixing. 2. Neutrino mixing means that different types of neutrinos can transform into each other. Conclusion. Neutrinos are thought to be influenced by the neutrino field. However, the existence of the neutrino field has not yet been experimentally proven. Scientists are conducting research to confirm the existence of the neutrino field. Neutrino field versus Higgs field. Key differences. While both the neutrino field and the Higgs field are quantum fields that influence the mass of elementary particles, they differ significantly in their mechanisms and roles. 1. Role. 1. Neutrino field provides mass to neutrinos. 2. Higgs field, through the Higgs mechanism, grants mass to other elementary particles, for example, W bosons, Z bosons, fermions. 2. The Higgs field itself does not possess mass. 2. Interaction. 1. Neutrino field exerts an extremely weak force, even weaker than gravity. 2. Higgs field possesses a relatively strong force, much more potent than the neutrino field. 3. Associated particles. 1. Neutrino field interacts with neutrinos. 2. Higgs field interacts with the Higgs boson, discovered in 2012 at CERN's Large Hadron Collider. 4. Mass generation. 1. Neutrino field imparts a very small mass to neutrinos. 2. Higgs field confers a range of masses to different elementary particles. 5. Symmetry. 1. Neutrino field, its existence does not break gauge symmetry. 2. Higgs field, its existence breaks gauge symmetry and generates mass via the Higgs mechanism. 6. Observability. 1. Neutrino field, extremely difficult to directly observe. 2. Higgs field, can be indirectly observed through the Higgs boson. 7. Research status. 1. Neutrino field, still an incompletely understood field. 2. Higgs field, actively studied since the discovery of the Higgs boson. Conclusion. The neutrino field and the Higgs field play crucial roles in the mass of elementary particles, yet they exhibit distinct differences in their mechanisms, roles, interactions, associated particles, mass generation, symmetry, observability, and research status. Quantum field theory, a primer. Quantum field theory, QFT, is a quantum theory that describes physical phenomena using fields. It serves as the theoretical foundation for fields such as particle physics and condensed matter physics. QFT is based on the wave-particle duality of particles. In particle physics, particles like photons, electrons, and quarks are interpreted as excitations of quantized fields. For instance, electrons and positrons are represented as excitations of the electron field. QFT has been successfully applied in the following areas. Particle physics, the standard model, based on QFT, explains the fundamental particles and their interactions that constitute the universe. Condensed matter physics, QFT is used to describe the electrical, magnetic, and thermal properties of solids. Astrophysics, QFT is employed to explain cosmology, stellar evolution, and black hole properties. QFT stands as one of the most significant theories in modern physics, serving as an indispensable tool for understanding the universe. Key concepts in quantum field theory. 1. Field, a physical entity that exists throughout space and time. 2. Particle, an excitation of a field. 3. Quantization, the process of describing particles and fields using the principles of quantum mechanics. 4. Interaction, the interaction of two fields manifests as an interaction between particles. Applications of quantum field theory. 1. Particle physics, standard model, quantum chromodynamics, quantum electrodynamics. 2. Condensed matter physics, electricity, magnetism, heat, semiconductors, superconductors. 3. Astrophysics, cosmology, stellar evolution, black holes. The future of quantum field theory. QFT remains a developing theory. While the standard model explains all known fundamental particles and their interactions, there are still unsolved problems. For example, gravity is not explained by QFT. QFT serves as an essential tool for understanding the universe. It is expected that QFT will continue to evolve and contribute to solving fundamental problems in the universe. Additional information. 1. QFT has been instrumental in the development of new technologies, such as lasers and transistors. 2. QFT is a complex and challenging subject, requiring a strong foundation in mathematics and physics. 3. There are many different approaches to QFT, each with its own strengths and weaknesses. Despite its challenges, QFT is a fascinating and rewarding field of study that offers a deep understanding of the fundamental workings of the universe. Introduction to gravity field theory. Gravity field theory is a physical theory that describes the relationship between the geometrical structure of spacetime and mass and energy. Gravity is one of the most fundamental forces in the universe and influences various phenomena, including planetary motion, stellar birth and death, and black hole formation. History of gravity field theory. The first scientific explanation of gravity was provided by Isaac Newton with his law of universal gravitation. Newton's law states that all objects with mass attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. While this law was successfully used for centuries, it was found to be inaccurate in situations involving very strong gravitational fields or very high speeds. In the early 20th century, Albert Einstein presented a new description of gravity with his theory of general relativity. According to general relativity, gravity is a consequence of mass and energy warping the geometrical structure of spacetime. This warping affects the motion of objects. Key concepts in gravity field theory. 1. Gravitational field, the force created by mass and energy that warps the geometrical structure of spacetime. 2. Spacetime, the combined concept of space and time. 2. General relativity states that gravity bends spacetime curvature. 3. Curvature, the extent to which spacetime is bent. 3. The greater the mass and energy, the stronger the curvature. 4. Absolute parallel transport, when an object is moved from one point to another in spacetime, its direction may change due to curvature. 4. This change is called absolute parallel transport. 5. Geodesic, the shortest path between 2 points in spacetime. 5. Objects generally follow geodesics in their motion. Applications of gravity field theory. 1. Astrophysics, used to study black holes, neutron stars, pulsars, dark matter, and dark energy. 2. Cosmology, employed to investigate the expansion of the universe, the Big Bang, and the future of the universe. 3. Satellite orbit calculation, used to calculate the orbits of artificial satellites. 4. GPS, utilized to enhance the accuracy of the GPS system. The future of gravity field theory. Gravity field theory remains an evolving field. While general relativity successfully explains many phenomena, it is not compatible with quantum mechanics. Quantum gravity theory, which aims to unify gravity and quantum mechanics, is expected to contribute to solving problems like the black hole information paradox and the initial conditions of the universe. Additional information. 1. Gravity field theory is a complex and challenging subject, requiring a strong foundation in mathematics and physics. 2. There are various approaches to gravity field theory, each with its own strengths and weaknesses. 3. Despite its challenges, gravity field theory offers a profound understanding of the fundamental workings of the universe, making it a fascinating and rewarding field of study. Improvement notes. 1. Added a more detailed introduction to the history of gravity field theory, including Newton's law of universal gravitation and Einstein's theory of general relativity. 2. Clarified the definitions of key concepts such as gravitational field, spacetime, curvature, absolute parallel transport, and geodesic. 3. Expanded the explanation of the applications of gravity field theory in different areas. 4. Provided additional information about the future of gravity field theory and its challenges. 5. Overall, the response is now more comprehensive and informative, offering a deeper understanding of gravity field theory. Electromagnetism, a comprehensive overview. Electromagnetism encompasses the study of electric and magnetic fields, their interactions, and their effects on matter and energy. It is a fundamental concept in physics with far-reaching applications in various scientific and technological fields. Key concepts. Electric field, a region of space influenced by an electric charge, exerting force on other charges. The field lines depict its direction and strength. Positive charges repel, while negative charges attract each other in an electric field. Magnetic field, a region of space influenced by a moving electric charge or a permanent magnet, exerting force on other moving charges or magnetic materials. The field lines illustrate its direction and strength. Magnetic field lines never intersect. Electromagnetic induction, the principle that a time-varying electric field generates a magnetic field, and vice versa. This forms the basis for many electrical devices like generators and transformers. Electromagnetic waves, propagating disturbances in electric and magnetic fields, carrying energy through space. Light, radio waves, and X-rays are examples of electromagnetic waves. Properties. Vector field, electromagnetic fields are vector fields, having both magnitude and direction at each point in space. Maxwell's equations, 4 fundamental equations that describe the behavior and interactions of electric and magnetic fields, including Gauss's law for magnetism, Faraday's law of induction, and Ampere's circuitol law with Maxwell's addition. Wave nature, electromagnetic fields can exhibit wave-like behavior, characterized by wavelength, frequency, and speed of light. Energy and momentum, electromagnetic fields can store energy and possess momentum, allowing them to exert forces on objects. Applications. Electrical and electronic engineering underpins the operation of motors, generators, transformers, electronic devices, and power systems. Communication provides the foundation for wireless communication, satellite communication, and fiber optic communication. Medical imaging forms the basis for MRI, CT scans, and X-rays, enabling non-invasive diagnostic techniques. Scientific research facilitates diverse scientific investigations, including measuring the speed of light, analyzing atomic structures, and studying material properties. Future of electromagnetism. Electromagnetism continues to play a crucial role in modern society, with ongoing research aiming to advance our understanding and applications in areas such as 1. Wireless power transmission, efficiently transmitting power over long distances without wires. 2. Metamaterials, engineering materials with tailored electromagnetic properties for specific applications. 3. Quantum electrodynamics, unifying electromagnetism with quantum mechanics to understand phenomena at the subatomic level. Electromagnetism is a vast and fascinating field with significant implications for our understanding of the universe and technological advancements. Its continued exploration promises to yield groundbreaking discoveries and innovations in the years to come. The flow of the cosmos is an endless dance, where forces intertwine, embracing fate's trance. Wrapped in the dreams of the neutrino field's embrace, guided into the depths of Higgs' dark grace. Electromagnetism and quantum weave delicate grace, while whispers of gravity gently guide our pace. Enshrouded in secrets of antimatter and dark, lies tales concealed in the universe's arc. A radiant future in the gaze of dark energy. Woven by string theory, our dreams set free. The universe's song, eternally streaming. In the infinite dance of forces, we're gleaming. Thank you for watching until the end.